So I don't have to explain why it's called TASE, right? This conference at least. But this particular effort started off as something that uh, built on top of what MapReduce had built over the years in Hadoop, which is to have a way of having a data pipeline where you have a constant stream of data coming in, being processed, being queried, and being consumed by people in various ways. So, TASE at a very high level is a distributed execution framework which lets you process data, and it uses something that is called a directed acyclic graph to schedule things. And it is written to be very, very flexible and customizable for anybody to use for the special cases. It's in some sense a generalization of all the things that people have asked for over the years from MapReduce. And it is built on top of Yarn, which is what Hadoop 1 to Hadoop 2 was a shift from. To clarify for most people, I'm assuming that almost everybody here has heard of Hadoop. How many of you use Hadoop? Okay. How many of you use Hadoop 2? Okay. Smaller hands raised. So Hadoop 1 was a single purpose framework. It had MapReduce and had HDFS. It had two things which you could use with each other to do everything you wanted to do. The other side of this problem was that if you wanted to do something else, you had to convert whatever you wanted to do into a MapReduce job running on top of HDFS, right? This was apparently enough for people to build a large number of things, including an SQL engine called Hive, a data processing system called Pig, and the basic MapReduce thing that people wrote Java applications on top of. And that worked very well. It was scalable. It did a lot of things. But what it didn't do is it didn't let people make framework decisions that benefited your workload, right? If you had a workload where you're processing data continuously, for instance, you couldn't actually host it on MapReduce. You'd have to actually start a job to start processing data, and the job would end and the data processing is over, right? So Yarn came on top of this particular thing, or rather below MapReduce, in a way that lets people run various kinds of workloads on the cluster without having to actually make assumptions like it is written in Java, right? MapReduce had that a strong assumption. So Yarn lets you do things like let you run applications which are not written in Java, written in any language you want. But on top of that, you have to build error handling. I think this statement has been made many times in the last 2 days that distributed systems are hard, right? And distributed systems that perform fast and are scalable is doubly hard. Like picking one of those two is really easy. Like I'll have a fast system that fails occasionally is easy in relation to building a system that is scalable and fast. And you ended up with a bunch of data flow mechanisms that were traditionally written using MapReduce, which needed a sort of new home, right? That is where TASE really comes in. And the key innovation that lets us do this is that the bottom layer is Yarn, which splits away the execution part from the Hadoop cluster part. So you run a Yarn cluster, you can run Storm on it, you can run HBase on it, you can run Pig on it, Hive on it, MapReduce on it. That used to be the same thing before. Now we put in a layer in the bottom called TASE that lets us build some things that MapReduce used to provide, but specifically tuned for things like Pig and Hive. Now, the fact that MapReduce is slow has been said by so many people over the last 5 years. And the solution most people have is to go back and invent something completely new, right? People have tried to build like SQL engines which do not use MapReduce. And arguably, there are some arguments in favor of building SQL outside of Hadoop. But if you want to do SQL in Hadoop, right, you had to actually split away from MapReduce and lose all the nice things that people have done put into MapReduce over the years, right? Nobody's going to, like, if you build something new today, a new architecture today, it is very difficult to get somebody like Yahoo or Amazon or Google to actually test it on like 10,000 nodes and actually figure out what decisions that you made for 100 nodes work for 10 nodes and how many of them work for like 10,000 nodes. So people use the word legacy to describe MapReduce, right? I want to use the same word to describe MapReduce, but as somebody would describe a legacy that you inherit, right? It's a large amount of collective work and time spent into optimizing and fixing things at scale that we do not want to lose in the process. So, on top of that, Hadoop had a lot of security work done for MapReduce on Yarn, which we didn't want to lose when we built Thais on top of Yarn. So, Thais. So Thais addresses really like three main problems that MapReduce had. First, you had to convert everything you had to do into a MapReduce job. So what if what you wanted to do didn't actually fit into map or reduce? What if you wanted to put something in the middle, right? You had no option of living outside that particular constraint framework. And in some sense, people built sequence of MapReduce jobs chained to each other as a way of describing what they actually want to do, right? And this is not the most elegant way of doing things, but as long as you only had MapReduce, you had no choice but to use that to run it on a Hadoop cluster. So expressing the computation better is the first thing that we looked at. Second thing is performance, because as people said, MapReduce is slow. Some of the slow parts are because you couldn't express what you wanted to do in MapReduce, right? But the next part is the actual runtime. Like if you could express what you wanted to do with MapReduce, say you wanted to run a map, a reduce, and then a reduce, could you do things far smarter in like something like this, which lets you do the fact that a distributed system has distances between nodes, right? Like running on 20 nodes basically means every node is equally accessible to every other node. When you go to 40 nodes, half the nodes have twice the bandwidth to half the nodes, or their half, and the other ones have to go across the switch, right? So could you use information that you knew about the future jobs that you're going to run on this data and plan things so that you can run things faster? Plus, we discovered that there is a bottom 20 seconds or so in MapReduce. That is a lot of things that you did in MapReduce that you really do not have to do if you were running the same job jar every single time. So MapReduce was written in a time where you would write a Java application using MapReduce, you would run it. Whereas we are living in a time where you would write Hi or Pig, which is built using MapReduce or Thais, and run the same jar file multiple times, hundreds of thousands of times for each job, right? The last part is something that people do not usually appreciate about Thais, is that Thais was written for operational simplicity. That upgrading a MapReduce cluster, say from Hadoop 1 to Hadoop 2, is a ridiculously hard challenge. It requires you to like stop things running on it to do that. And when you run 10,000 machines, stopping 10,000 machines and starting them up will take 2 days, right? So for 2 days, if you say that your cluster is not operational, it is not an acceptable thing. So you want a way to deploy Thais in a way it doesn't require either an admin interaction and without requiring anything other than just a file being copied into a location, right? So the significant advantage Yarn brought us is that Yarn lets us isolate different versions of Thais running in the same cluster from each other. So I can run Thais 0.4, somebody else can run Thais 0.5, and somebody else can run their own version of Thais on the very same cluster. Whereas in MapReduce case, the runtime was part of the cluster install, right? So if you had to upgrade the runtime, you have to upgrade the cluster. So the simplifying operation part, we use the most common mechanism for sending files across a Hadoop cluster, which is to copy it to HDFS. My battery is dying. No, just no. Slow, slow. Yeah. Okay. So the simplifying operation part basically we use a pure Yarn application, right? So that as long as the only deployment that you ever make is Yarn, you deploy a Hadoop 2 cluster, and then you do not deploy Thais after that. Thais is something that you can run as part of a single job. So it doesn't require an admin user to actually go and install Thais in a cluster. And this is a big deal because it basically lets us coexist with the MapReduce job, with an HBase job, with a Storm job in the same cluster. Next, how do we express a computation? So MapReduce used to be map and reduce connected using one edge, which is always sorted. For example, some people don't want sort. Some people want to put something in between map and reduce, like in this particular case, right? So we tend to have a generalization of map and reduce as a bipartite graph of two vertices connected to each other, right? Something like this. So we took map reduce and wrote out its assumptions that map processor reads data from a split generator and produces on file sorter output, right? And the next stage actually figures out that it is supposed to merge it, so it runs shuffle merge input, in this case legacy, because it assumes some things about the input format. And the reducer is actually an independent vertex which actually has no real logic saying it's a reducer or a mapper. We just call it that because it makes it easy for people to say. Now, it is not immediately clear how when we go from MR to this generalization, how things change. So, let me ask a question. How many of the people here run more than one join in a Hive or big job? So for all those people, next slide would be very interesting. So this is a 7 or 8 way join that you actually run as a single job in Tace. The split apart from just being MR to being able to connect vertices in any way you want basically lets us express the fact that we are doing this particular multi-way join directly into Tace. So Hive gets to not have to figure out which point to actually split up maps and reducers, only where the vertices end. And I'm not sure it's very readable, but there are some edges in this particular image which are not sorted, right? And things like that in the DAG API basically lets us set up a vertex graph that actually describes what we actually want to do rather than trying to fit in what it would have done in MR. Now, this is not an easy translation. It took a while for Hive to catch up to using this. Pig is using this now. Then at the bottom layer of things, there's the runtime API that actually forms the interface between the edges and the data, right? There's some sort of assumptions made about what things people who are familiar with MapReduce already want. Like I said, on-file sorter output. Like on-file sorter output is no different from in-memory sorter output, right? The only difference is that on-file sorter output is what people used to use. So if you wanted to just replace your MapReduce pipeline of multiple stages into this, you just used on-file sorter output in every edge. So the API sort of looks like this, and I do not know if this particular join graph makes any sense to people, but the traditional way of doing MapReduce joins is to go through both sides of the table in the same map task and do a lot of magic in the runtime to write an integer which says, is it from the left hand or the right hand, and sort it based on the key and that integer and then merge it back and do all kinds of magic. This is far cleaner, far more understood, and far easier to schedule, because we know that if the left hand side produces 50 GB of data and the right hand side produces 120 GB of data, we can actually figure out how many data items are required and then how many processes are required in the next stage. So Taze, what it does is it takes this logical plan and produces a physical plan at runtime. Now, people who have used MapReduce would know that you would run something called a split generator, right? The split generator is something that is hard-coded. It's like, how many splits of data do I process in parallel? And what Taze lets you do is Taze lets you decide those things after getting on a cluster instead of before. This basically means you get to figure out, for example, how big is my queue? Do I have 200 containers available or do I have 100 containers available? I can potentially generate 200 splits from like the 50 GB I have, or 100 splits depending on how many containers I might likely have. And by taking information from the left hand and right hand side independently, it can figure out how many join tasks I actually need to run again at runtime. Now we put like safety bars in this, so we let people set a min and a max and let Taze figure out the difference between min and max, because just in case all the data is going to come from the last 10 mappers you ran, right? You do not want to get hit by a pessimistic assumption. On top of the edge part, there is the actual processors, which is the vertices. The vertices have like two ends, the processor of sorts, we have a classical map and classical reduce processor, which both end up having very standard input and output specified. Now, the real advantage between the classical reduce and the intermediate reduce, which is the light, this particular one, is that this is not going to HDFS, right? The output that I'm generating from this particular reducer is not going to HDFS. In map reduce, every single output that a reducer produces, for traditional case at least, actually goes directly into HDFS. Now, this is not really a big problem for most people, except when you try to figure out what happens when you have 4 MB of data from 600 mappers, 600 reducers, right? You'll end up having a large number of files. So, to say it in a different way, I should explain. Everybody's familiar with SQL, right? In this case, so there is a select average case with a group by that we're joining in something else, right? In a traditional MapReduce case, Hive cannot actually figure out how big the data will be before it actually starts to do something like this. So Hive has to actually run that query, then run something on the server or gateway box you're running, and then send it back again to the cluster to do close. Now, this would make sense if you're running it on a single machine, which is a gateway machine within the cluster. But for production use cases, for a secure cluster, you are never really given access to the cluster. The admins have access to the cluster. People running jobs don't have access to the cluster. So this operation is really slow because you write to HDFS, come back, decide to do something again, generate splits again, go back to the cluster, ask for resources, start doing work again. So we have something called a broadcast edge, which describes not whether it's sorted or not, but about how data is distributed, right? The traditional MapReduce edge is called a shuffle. It is called a shuffle because you generate 100 items from each and give each item to each reducer. So it's like a merging of cards in a shuffle. Like it's like this. What we do in this particular case is something called a broadcast edge, where all tasks get all the data generated. So the average number that we calculated is sent to all tasks because it's a very small amount of data. Instead of forcing a join that is actually using the HDFS layer. The next important part where TASE actually becomes more important than how a simple DAG scheduler works is TASE supports something called Vertex Manager plugins and Edge Manager plugin. The Edge Manager plugin actually lets you decide which data item gets, which task gets what data item, independent of what TASE decides. So the application can actually write something that will route data depending on information it has. Now, this particular one is actually a join from a sales table to an inventory table when they're both stored, bucketed by item, right? If I know that bucket 0 of store sales and inventory 0 of store sales is the only one I need to join, I will actually have, like, if I divide it by 100, I'll have 1% of the data that needs to be read by a single task to do a join. So it lets me do something which I couldn't do before, like a map join with distribution, and to be able to actually say duplicate data to different places. So something similar used to exist in Hive before as well. The biggest pain that it had was that after you decided that bucket 0 will be processed by one task, it doesn't matter how big bucket 0 is. If bucket 0 is 200 GB, 200 GB is going to go through that one task. So it was potentially slower to do the fast logical way than it was to do the slow logical way, right? So this basically says that from inventory, I'll take bucket 0, give it to everybody who's processing bucket 0 of store sale. So store sale suddenly became a distributable problem, right? So that 200 GB suddenly became distributable. And in general, taking a slow problem and distributing it anyway makes it faster. Taking a slow thing and making it faster and distributed is always a win. So being able to write these custom edges is something that no other DAG framework that people popularly use support. And this is a big win for things like select star, where x less than 10, limit 10. You want to run the task until you calculate 10 results globally. You do not want it to go through all data, collect 10 results from all data, and then finally decide to read only the first 10, right? You want to exit when you hit the first one. The very first task finds 10 records, you want it to exit then, not go over the remainder 200 GB. right? Being able to put fast exit paths is why edge managers and vertex managers make Tails very, very flexible. The other part that most people don't know about, and this is a SQL-ish aberration that Hive has, is that Hive allows you to run one query and insert into multiple outputs, right? This basically means that if you have a very large table, you can calculate many different queries on the same large table in one pass. So for most reporting use cases, you will have today's data. I want to generate 15 different reports, right? The way most people do it in the traditional SQL world is to run a query that goes over the data once and then do the same operation 15 times. What this lets you do is this lets you go over the data once, generate those 15 outputs and send them to independent reducers later. This is because we are not limited to, for a given mapper, there is only one reducer. We've broken away from that limitation. So it lets you do things far more parallelly because you do not have to write to HDFS in the middle. And I might be banging on why HDFS is slow for a while. But HDFS is not slow because HDFS is bad. HDFS is slow because HDFS offers very strong guarantees. If an entire UPS for a rack dies, HDFS still has to keep data alive. So what HDFS does is that when data is generated and returned to HDFS, it will write to approximately 3 machines. It will try to write to more if any of them fail, but it will write to 3 replicas. One of those replicas is guaranteed to be in a different UPS or rack section from the one you are currently in. Now, it doesn't matter at small scale, all these delays, because if you have 20 machines and one rack, or alternatively, if you're an EC2, right, and you haven't figured out how to use like distribution of AWS regions for this, it is not particularly slow to write to 3 machines versus writing to 1 machine. But when you have to cross a rack boundary or cross 2 or 3 rack boundaries, it actually really starts to slow down. Tails doesn't need such strong guarantees on data because Tails knows exactly what to run to recover that chunk of data in this particular thing, right? If one chunk of data, output of one reducer gets lost or a machine gets lost, it knows what all things to retry, right? And being able to reliably retry is another one of those hard scalable problems which affects your ability to be really fast. But there is no real value in being really fast 90% of the time and not working 10% of the time, right? It is not something you can rely on in a production use case. Then you get into the really exotic things of what you can do. So in a number of scenarios, you'll go over the same data multiple times to do different things, right? Sometimes you might not be able to do all of it in one go. You'll have to go over all the data, then go over all the data based on the information you collected from it, right? So Pig had something called skew joins, where if a given date has 100 times the traffic of every other date, if you did a uniform join, that whoever gets that date will be horribly slow, right? So to be able to split apart that particular date into like different buckets or different processes, Pig comes with something called a skewed join. So you'll be able to say, my data is this. Most of the time it says it's not loaded, but make sure that when I do a join, distribute the case that has the largest load. It used to be that Pig would go over the data once, generate a data file, read it back, and then decide to do the partition and join part later, right? What Tails lets us do, it lets us put one-on-one edges that lets me calculate an aggregate and give data to the next stage at the same time. In fact, we use the information that Pig gives saying that it's a one-on-one edge to make sure that the second job runs on the same machine as the first job, provided there's capacity. Now, the real advantage of that is the data never moves over the network, which means that as you add more machines to the cluster, it doesn't get slower. If you use a completely connected pipeline system which moves data from one end of the query to the other end of the query, you will end up moving a lot of data over the network, and it wouldn't matter so much if your data queries were like narrowing down the output. Like if you pump data in and pump the exact same amount of data out, like in this particular case, like you're doing a join without any selection, right? You will end up having a significant number of problems moving data over the network if you just randomly distribute it, right? Being able to schedule the next task on the same machine and not having to move it over HDFS, both actually make this significantly faster for Pig. So there is one thing that I didn't talk about is that Yarn has something called an application master. So the reason Yarn made things like this possible is because unlike MapReduce had something called a job tracker which should track every job, right? One, that is a horrible way to do like a distributed system because having a central thing that keeps track of everything that happens in a cluster is not very scalable. So Yarn splits it up into two things, a resource manager, which is generic, and an application master, which is application specific. So Taze as an application master, which understands everything I talked about earlier, while the MapReduce application master doesn't have to know anything about what Taze does, right? So you can have the isolation of two different architectures in the same Yarn cluster because the resource manager is the same for both. Both of them need memory, both of them need CPU, both of them need disk, right? Now, the performance gains are mostly to do with the fact that now we are doing exactly what Hive and Pig wants. We are not doing stuff that MapReduce has that Pig wants to try using, right? One of the few good things that happened in this particular process is that people from the Hive and Pig community worked very closely with Taze to tell us what they were missing in MapReduce and told the Taze community to build it, right? That close interaction to try describing what Taze and Pig and Hive and cascading have to do together has made the fact that the DAG expression is as close to the best case scenario for all these applications. Now, the next part is efficient use of resources, right? There's a lot of things that you could do differently if you knew what you were going to do later. Like the co-scheduling mechanism I described earlier was that I know I'm going to read this data in a few seconds. I know that this is the machine that I'll send that task to. In MapReduce, I would let go of that machine when my task completes on that machine. So Taze, because it knows you're going to do something later, Taze can actually send the new task to that machine and have it waiting before all its dependencies accumulate. So if you have a one on an edge, it will finish this edge, start the next task if there are no pending tasks for the first stage, right? Being able to use global information to do task scheduling makes a lot of these things faster if you pay attention to all the details. The next part is that at runtime, being able to change the plan you made, like MapReduce. After you decided what your MapReduce plan is going to be, you cannot change it after the query starts or the run starts. After it starts and you realize I could have done something differently better based on information I got from the first phase of the task. There is no way you can influence the reducer after you start the mapper, right? As you saw earlier in the edge manager and the vertex manager cases, we actually have a plugin mechanism which lets you control parallelism, edges, and scheduling models of each task, each vertex independently of the previous vertices. So the predictability of this thing has a very different angle to it as well. So usually if you're submitting a single query, all of it is going to run as the same job, right? In Taze. And the only reason we can assume that is because it's all going to run as the same user in the same security context in the same queue, right? If you had to run 3 separate jobs, every time a job finishes, you'd have to give up all the resources you got for that job. Then you have to pick up new resources. And for that, you'd have to enter in a queue where you're behind everybody else. Imagine running a 3-stage process where after the first 2 stages, somebody else runs their first 2 stages, right? This is not so bad for utilization of the cluster, but this is really, really bad for your query and their query. It would be better for both of you to get out of the cluster fast by making sure that whatever resources you need for the next stage are already kept from the resources you collected for the previous stage. On top of that, within a stage, within a DAG, we actually reuse JVM to spin up. So people say Java is slow, right? And it's slow if you hit the GC, right? If you allocate in a for loop, it is slow. But Java is not slow after the JIT kicks in. But the problem is, for the JIT to actually kick in and get enough information to figure out what you're doing, you need something that runs for a few seconds, right? And you usually do not get things that run for a few seconds. Obviously, the goal of Thales is to actually run things in like 1 or 2 seconds. So if I'm going to run my entire query in 2 seconds, I obviously do not get any benefit from the JIT, right? And that's bad. So what we do is that we actually do not tie up the task with the JVM. We have the containers as a completely independent entity from the task. And each task asks for what it should do from the application master and does it and gets out. And the container stays alive. So imagine you're doing a table scan in Hive, like where clause. Filter operator would get progressively better as you just kept using it, right? You wouldn't lose that information every time a job finished. This is compounded by the fact that if you run Hive Server 2 in the BI mode, we actually keep a bunch of live sessions. We keep a few sessions alive, which have 10 or 15 containers alive, so that when you fire a very small data query, it actually executes immediately and gets out. It like executes in like 4 or 5 seconds. And we have code in Thales today, which does things like keep 1 container per node, right? Instead of trying to say keep 10 containers, right? You can say keep 10 containers, but never have 2 containers in the same node, if possible. If you have more than 10 machines, make sure that at least all of them have it. This gives you a lot of locality. Not only that, if you run, a map join is a very classic case in Hive where you load up a small dictionary and stream a big table through looking for whether the keys that you find are in the dictionary, right? An example would be you're trying to join store sales with a location store data, right? Find all stores which are in this particular state. Find me all sales that happen in that state. The way MapReduce Hive used to work is that it would start up, it would load this data, it would go through the big table and then exit. What Thales does is Thales says, am I going to run a different chunk of store sales before I exit? If Thales knows I'm going to scan through store sales again, it will not drop the state data. So that when the next one comes in, you don't have to go through the effort of loading data back. Whenever the vertex changes, it will actually drop this data. So when map runs, until map is done, all this data is actually kept in memory. So this basically means, there's no color. So this basically means when map2 runs next to map2, it is faster than the first map2. Because this guy doesn't have to actually load any data from memory, right? The core engine has more things than what I described. It does priority of things. It lets you override a ridiculous number of things that it is actually hard to use. But in the general case, what we have figured out for vertex managers and edge managers and the input and output phases, we have built a bunch of library of things that you can compose in any way you want, right? Now, most of what I talked about had to do with how we designed, what trade-offs we made while building this. This is before and after for MapReduce, right? This is not a trivial query. It is a large number of joins on 10 TB data on 20 nodes, each of which have 64 GB RAM, which is not really a big cluster, and which have 4 HDFS disks each. I wanted 6, but fine. So this is sort of the query 68 at this point never finished in MR, which is after 7 hours, I think, just killed. But what the improvements that you've gotten so far over the period has been a significant amount has been being able to express what you want as a DAG and being able to run it really, really fast based on all the runtime improvements I talked about. So if the runtime gave you 2x and the plan gave you 10x, that is actually 20x, even though each of those two things really are not, well, people don't really conflate both those things together. Now, spend a lot of time with Hive, figured out what Hive needs, and suddenly looked at Pig because obviously Pig also has very similar requirements from MapReduce, which was never satisfied. Now, Pig did the simplest thing possible. Pig took its work plan and just converted it into map and reduce into into Tails. It didn't do any of the complicated uh, edges. It didn't do any of those things at the first. So most of these improvements that you're seeing do not use any of the complicated things that it used to do. And you might notice that all the work we did to make queries run in 4 seconds can also be read by queries that run in 4500 seconds, right? And a 3x gain in this means tens of thousands of servers not being bought, right? So Yahoo did this particular benchmark where they tried to figure out whether to use Tails or something alternative to MapReduce. And they found out that Tails was the only thing that relatively scaled to 300, 400 nodes and handled tens of TBs of data. Then, obviously, Hive, big. The next common use case people say is that MapReduce really sucks if you want to do iterative algorithms. If you want to go over data and run k-means and clustering, MapReduce is a really horrible way. And it's mostly because you have to go to the beginning of the queue, ask for containers, get a JVM, lose all context every time you exit a particular stage of your loop, right? So big guys built a loop unrolled k-means, not loop unrolled. Big did a very heavyweight loop of k-means, which was basically load data, run job, decide whether to run next phase, run job, run job, run job. It's not the most effective way of doing iteration, but even with such a simple thing, we got like a 15, 14x improvement in performance. Now, the one-on-one edges I talked about earlier basically lets you do iteration even faster, right? It lets you take your entire iterative job and you do not have to wait for the first stage reducer to finish. You can just run through a vertex group of 10 reducers before you exit, right? You can actually chain your reducers with one-on-one edges or tasks with one-on-one edges and make sure that the first one to reach the end leaves the cluster free for the other ones to do other work, right? Not being a selfish thing that takes up a land grab in a cluster is an important thing for people who run multi-tenant clusters. If you spun up a cluster for every job you did, you wouldn't need most of the stuff that is limiting us from getting to like very fast. But being something that does a land grab in Hadoop and takes up hundreds of GB and stays resident until the last thing exits is a very bad way of getting multi-tenancy and utilization. So one of the key things that we did in Tails was to decide that we are building this for really busy big clusters. We are not building this for a cluster which is going to have only a few boxes, and we are not going to connect from every box to every box, right? If you have 20 boxes, 20 square connections is not a lot. 400 square connections is a lot, right? The other thing is, Tails was designed to work better as the cluster gets busier, right? It is designed to work better than MapReduce as the cluster gets busier. It is because if you have a 4-stage operation, you do not go to the beginning of the queue every time each stage finishes. And the next is, if you have intermediate output between jobs, because you're not writing it over the network, you're not writing it across racks, you have less overhead for that operation. You are not bothering anybody who actually needs to move data across racks, right? And more importantly, if you run a significantly large cluster, you will end up having a name node which uses a significant amount of memory and which is tied to how many files you have. So the fewer files you write to HDFS, the better HDFS performs from the name node perspective. So the fewer small files I write, the better it is. And this basically helps me do that. And as the container use example said, like MapReduce traditionally used to work even if you threw hundreds of terabytes of data at it. So Tails is designed to actually work better and better as you throw more data at it because of the container use and the chip performance improvements we did. Plus, if you do not have that much data, if you had like 10 containers worth of data, you had the BI session pool lying there just to run those 10 container jobs. But those sessions are not limited to 10 containers. They can grow to 200 and shrink back to 10, right? Being able to grow and shrink elastically is very hard if you do an in-memory workflow, right? Because when you kill a container, what do you do with the data it has in memory? You either recompute it later or you lose it. Finally, for things like map joins and Hive, we moved a lot of work away from gateway boxes, which is the box you log in, or people running Hive Server 2. We moved that job into the cluster. Now, it doesn't actually speed up things a lot, but what it does is it prevents your Hive Server 2 from dying from load, right? You could run like 1 or 2 gateway boxes and they wouldn't die. And that is a big win if you actually have heavy production traffic at the same time from different people. So the real problem in a busy cluster is, what if you only get 50 containers and you have 8,000 tasks, right? So what we do is we pack everything as tightly as possible into the same containers. So this is container number 9, which is running all these tasks one after the other without unloading the JVM, right? To actually do this, we have to go through a lot of QA to figure out people who have made assumptions that they can allocate memory and not free it, right? Thankfully, Java is easy to debug that because the GC very clearly shows what objects are referred by whom. But after doing that, this was a huge win, because in a gang scheduling system where you wait, if you need 10 containers worth of memory, you wait for 10 containers before saying, okay, you can load data. Being able to say that I will run with 9 containers, but only a little slowly, is a bigger win for production use cases than actually waiting for 10 containers to become completely available. So adoption is currently Hive, Pig, cascading. And the good thing about cascading is, when you cascading supports, we automatically get scalding and Scala support, which will help a lot of the ML iterative use cases I talked about earlier. And bunch of commercial vendors are trying to use Taze instead of MapReduce, because I think for hundreds and thousands of TB of data for a petabyte warehouse, that is one of the this is one of the ways you will be able to survive in a busy cluster. And we've got a bunch of things coming up. We are building an in-memory HDFS layer. We are building all the collections that we have built, the edges and things like that, so that people, when they come up with a new use case that we haven't run into, we'll try to generalize it and add it to Taze. We are planning to improve the co-scheduling, preemption, basically what happens when a cluster is 100% occupied, how to let go of the right things. And there's a huge community behind it. You can send the list to all the mailing list. This week we got off the incubator, and we are Taze. Any questions?
We have time for about 2 or 3 questions. 2, 3, 3 at most.
People asking questions raise their hands.
If anybody has any questions, now is the time to ask.
Oh, how is it different from Apache Spark? So Apache Spark is not a data processing system. It is actually something that combines data and processing into one thing. So it has RDDs which hold data in memory, and something that and code that runs over it, right? If you have a workload that fits entirely in memory for you, okay. So what are the USPs for Taze? So I can say this: everybody who's benchmarking against their product marks Taze as number 2, which should tell you that no matter which use case you're going to throw at it, it'll be good. But being number 1 at the expense of affecting production is probably a bad idea if you really want to scale. Yeah, so there's a question.